Hello and welcome back. This is Chem 302, video number 2 from chapter 15. We just have one learning objective for this video today, and that's to determine the number of proton environments in a given compound. When you finish watching this video, I suggest that you go ahead and from the chapter 15, the proton NMR problem set, you work problems 1 through 4 and check your answers before moving on to video number 3. Okay, let's get started. So at the end of last time, we talked about 4 important features of proton NMR spectra, and the first one was the number of signals, or the number of absorptions, or the number of resonances. And that tells us the number of proton environments that the compound has. So it will be very important for you to be able to look at a compound and decide how many proton environments there are so that we can predict the number of signals we expect to see in the proton NMR spectrum of that compound. So we're going to just practice problems where we're just assigning how many signals we would expect to see. So we'll start off with some simple compounds, and these are all acyclic alkanes and alkyl halides. So what we want to do is decide how many proton environments we have here in terms of how many electronically distinct protons there are. Anytime that you are trying to decide if 2 protons are equivalent, what you can do is replace each H for the ones that are in question with an X and then compare them. So for example, what I mean by that, so if I want to know, well, in this methyl group here, are these protons equivalent to the protons in this methyl group here? What I would do is say, okay, I'm going to take this compound and I'm going to replace one of these hydrogens with the group X. So CH2, CH2, CH3, and I left this as CH2 because I'm going to stick on an X here, like that. And then I want to know, and hopefully it's obvious that these 3 protons are in the same environment. Okay, and if it's not, you can still use this method to show that that is the case. All right, but now I want to know if these protons are equivalent to these. So I'm going to draw this again, and I'm going to replace one of these hydrogens with an X. Okay, so I've got my CH3, CH2, and now CH. I'm going to make this a 2, rip off one of the hydrogens, and replace it with group X. Doesn't matter what group X is, they're just the same groups here. So if you were to name this and name this, you would get the same name, right? If this was a bromo group here, that would be carbon number 1. If this was a bromo group here, that would be also carbon number 1. So what this means is that these protons and these protons are in the same environment. So I'm going to label this, these are going to produce one signal. So I'll call this signal A. And now we have here a methylene group, and I should be keeping track whenever I use terms that I assume that you, I can spell, that I assume that you know. I should try to just write them down to remind you. So this is a methyl group here, that's CH3, and then methylene group is a CH2 group, okay? So the protons that are part of that methylene group, well, a methylene group is different than a methyl group. So this electronic environment should be different than this electronic environment. So I'm going to say, okay, these protons make up signal B. So I have 2 signals that we expect for this compound, okay? So there's my answer. All right, we'll go a little faster now. So if we come over here and look at this alkyl halide, we have a methyl group, and a methylene group. So these 3 protons are all equivalent to each other. These 2 protons are all equivalent to each other. So this is going to be group A. This is going to be group B. So I've got 2 signals expected. Good. And then if we come down here, here's butane. Butane has 2 methyl groups. Both those methyl groups are attached to a CH2 that's attached to a CH2 that's attached to a CH3. So these are equivalent, so A and A. We have 2 methylene groups, and they're in identical environments as well. Why? Well, this methylene group is bonded to a methyl group and a methylene group. This methylene group bonded to a methyl group and a methylene group as well. Same environment, so they're gonna make the same signal. So 2 signals. Okay, let's see if we can do an example that doesn't have 2 signals. Let's come over here. So we've got a 5-carbon chain. This is propane. All right, so we've got a methyl group and a methyl group. Are they in equivalent environments? They're bonded to a string of 3 CH2s, or 3 methylene groups followed by a methyl group. So yeah, they're identical. If you want to do this method to check that, of course you can. I'm just going to label this A and A. And now we've got these 3 methylene groups. Are they all in the same environment? Well, hopefully you can see that these 2 are in the same environment. But is this one in the same environment as these 2? The answer is no, it's not. And you can demonstrate that to yourself by using this little trick here, okay, which I'm not going to do, but if you want to pause the video and do that to demonstrate that this is in fact a different electronically distinct environment, please do that. So we've got 1, 2, 3 signals here. Yay, something different than 2. Okay, all right, and then here let's take a look at this example down here. We've got 2 methyl groups, but they're definitely in distinct environments because this one is bonded to a CH, and by the way, before I forget, that's called a methyne group, is when you have a CH group. Okay. And this methyl group is bonded to a methylene group. So these are different from each other. So if I call this one A, I'll go ahead and call this one B. And if you're wondering, does it matter how you're labeling these, A, B, whatever? I could have labeled it 1, 2, 3, doesn't matter. Okay. The methyne group, this proton environment is different than all the others. So I'm going to go ahead and label that one C. And then here, this is the only methylenes. That has to be in its own unique environment. So that's D. So I've got 1, 2, 3, 4 signals here because I have 4 electronically distinct proton environments. Okay, so these were examples of straight chain alkanes and alkyl halides. Let's try something a little more challenging. So let's take a look at alkenes. Okay? And you can use that same technique I talked about earlier, replacing a hydrogen with an X and comparing the structures, or you can actually build the models and do the same technique. All right, so here we've got ethene, also known as ethylene. This is a plant hormone. So if you need your bananas to ripen, right, you set down a piece of ripe fruit nearby, or you put them in a paper bag with the unripe fruit, and this is a gas at room temperature, and this will help ripen your unripe bananas. Okay. So how many proton environments do we have here? So anytime you see planes of symmetry, which I see I've got several planes of symmetry here, you have to be really careful that you don't overcount the number of proton environments. So with this here plane of symmetry, if I imagine a mirror here, this is reflected back, that tells me that this proton environment is identical to this one, and this proton environment is identical to this one. So there's one plane of symmetry there. But then I also have a plane of symmetry here. So that means this proton environment is equivalent to this one, and this one is equivalent to this one. Well, what does that mean? Well, that means these are all equivalent. Okay? So you have one signal. And again, if you're scratching your head, use that X technique that I showed you earlier. Okay, here we have our another example. So this was an unsubstituted, and again, I'll just write that down to remind you. A term that I think you learned last semester. So there's just hydrogens attached to the carbons of the double bond, so it's an unsubstituted alkene. Here we've replaced one of those hydrogens with an alkyl group, so this is a mono-substituted alkene. Okay. All right, how many proton environments do we see here? So this proton environment is different than this one. How can I tell? Well, this proton is cis to the methyl group and this one is trans to it. So these must be in different environments. So I'll call this one HA, call this one HB. What about this proton? So this proton is on the same side as the methyl group, same side meaning of the double bond. And then we have cis to it, this hydrogen, trans to it, this hydrogen, but this is definitely in its own unique environment, so I'll call that HC. And then in the methyl group here, all three of these protons are in the same environment, I'll call that D. Okay, so I have 1, 2, 3, 4 signals, or resonances, or absorptions. Another term that I do want you to learn, because I'm going to be using it quite a bit in upcoming chapters, is the term geminal alkene. This is an example of a geminal alkene. So if you are a Gemini, perhaps you know the origin of that word to mean twins. Okay. So here we've got two of the same thing attached to the carbon of the double bond, right? The carbon-carbon double bond here. Alkene, carbon-carbon double bond. Geminal, meaning you've got twins, the same thing attached here. So these are geminal protons. And this is an example of a geminal alkene, okay, where you have two of the same thing attached to the carbons of the double bond. All right, so I'll go ahead and label these as geminal protons. And I could say this is a geminal alkene. Okay, let's come down here. We've got a cis alkene. It's di-substituted. And is it a geminal alkene? No, because I don't have two of the same thing attached to a carbon of the double bond. Okay, so we said this was di-substituted. Oh, we also said cis, right? Same side. And if you had used E for, sorry, zusammen is together. So this would be Z if you're using the EZ terminology. Okay, but getting back to this. So how many proton environments do we have here? Now notice there is a plane of symmetry, BAM, right? So with this plane of symmetry, I expect this proton environment to be identical to this one. So HA, HA, and this one here, B, B. Okay, so we're going to have two signals here. All right, let's practice a little more with this. And just a reminder, if things are getting tricky, you can also build models. So let's see, this one I happen to already make is of this one, this example right here. I'll go ahead and put it like this. Flip that around. So if I wanted to really test to see how are these different from each other, what I could do is I could rip off HA in one of them and stick our X on. And then in my other model, I'll rip off the other proton that's in question of, we're asking ourselves, is it equivalent? Stick this on and then say, okay, are these identical? So if I try to superimpose them, it's clear these red balls, the X's are not lining up. So no, they're not. So they're in different proton environments. Okay. Let's do some more examples. Let's see here. We have, what type of alkene is this? We have 1, 2, 3 alkyl groups bonded to the carbons of the double bond. So this is a tri-substituted alkene. Is it a geminal alkene? Well, it doesn't have geminal protons, but it's geminal in terms of the methyl groups. So these methyl groups are geminal to each other. Okay, now they're not geminal to this. Okay, so we could call this a geminal alkene in terms of the methyl groups being geminal to each other. Okay, number of proton environments, right. So I don't see a plane of symmetry here. I don't see one here. So these two must be in different environments. So this is A and this is B. And again, you can use that little X trick. You can also say, well, here you have a methyl group that is trans to this one, and this one is cis to it. So these are not in the same environment. Okay, and so here we have C, and then this one would be D. So I've got 4 signals. Right. Okay, and just a reminder, I know in last semester you learned a little bit about alkene stability. So recall that a monosubstituted alkene is less stable than a disubstituted alkene, which is less stable than a trisubstituted, which is less stable than a tetrasubstituted. You probably already know that, just a reminder. Okay, let's take a look at a geminal alkene here. We've got geminal protons. And these chloro groups also happen to be geminal to each other. Do you see a plane of symmetry? Is it here? No, it's here. Okay. So these protons are equivalent to each other. HA, HA, no protons over here. So there's just one signal. Okay. All right. So make sure that you know what geminal protons are and what a geminal alkene is that will come up later in the next chapter when we talk about aromatic compound. Actually, again, with further on in this chapter, you're going to see it again. Okay, let's take a look at cyclic planar alkanes, so cycloalkanes that are planar. And so I'm only giving you examples here that are 3-membered and 4-member rings. And that's because I'm specifically looking for, whoops, not cyclic, planar meaning flat. Okay, so these need to be flat. So just like around the carbon atoms of a carbon-carbon double bond, you don't have that free rotation. Okay, when you're dealing with a ring, the carbon atoms in the ring, right? You don't have free rotation around them. I'm choosing just the 3-membered and 4-membered rings again because they are perfectly flat. Starting with 5-membered rings and up, right? You're going to have different conformations, and that really throws a kink in determining the number of signals. So we'll stay away from those. All right, so let's give these a go. So here we have cyclopropane, and we've got a skeletal structure here. So I'm going to go ahead and fill in the hydrogens. Okay, lots of planes of symmetry, right? I have a plane of symmetry here, and then in the plane, right? So if in this flat triangle, I have protons sticking up and protons sticking down. All of these proton environments are going to be equivalent. So I'm going to have one signal. Okay. Over here, we have chlorocyclopropane. Let's fill in the hydrogens. And then let's label our environments. So this proton environment is definitely unique. since it is bonded to a carbon that's bonded to a chlorine, and none of the other hydrogens are like that, so I'll call that HA. This proton environment, so attached to a carbon next door to the carbon with the chlorine, that should be equivalent to this proton environment. Same thing, they're on the same side of the ring as the chlorine, both of these, so I'll call these HB. And notice here there is a plane of symmetry running through here. Okay, so these should be equivalent. And they're going to be different from these, but these two are equivalent to each other. So this is HC and HC. So we have 3 signals here. And then our last example here, we have methyl cyclobutane. This methyl group is a unique environment, so I'll call that HA, label that as HA. Here is another proton that will be labeled HB. That'll be different than the rest of these since it's the only one with a methyl group attached to the carbon it's attached to. Let's fill in the other hydrogens. So we know how many there are. Okay, so let's see. Is this proton environment equivalent to HB? No, since this doesn't have a methyl group on it. So I'm going to call this, we're on C now, there's HC. And so this is going to be unique D. We've got here E, E, F, F. Let's see, is that right? We've got 1, 2, 3, 4, 5, 6. Good, 6 signals. Okay, all right. So you need to practice this. Make sure you get really fast at doing these. Up next, in the next video, we'll start in on talking about chemical shifts. We'll take a look at that chemical shift table again. We'll look at how the area under the curve relates to the number of protons making up the signal, whereas the chemical shift tells us about the nature of the electronic environment around the protons that are making up the signal. And then lastly, we'll talk about splitting, which tells us about the number of proton neighbors. So stay tuned.